Hi, I'm Scott Piggott. I work for the Lab for Atmospheric and Space Physics in Boulder. We have a couple co-authors on this. One of them is here. That's Mar in the third row. And so Python, well, actually, at the risk of blowing up my presentation time, can we talk about these name tags for a second? So what's up with the UTC time tag in hex bytes here? There's 3 of them, and they're for like Sunday at noon in UTC, which is really arbitrary. Like, did anyone write that? Can they explain it to me? Okay, no. All right. Well, I saw it. So anyway, Python, right? Like, we all like Python. It's a great thing. But the limitation is that it's really hard to, use Python in a flight software environment. Like, it's really great for scripting. It's really great for testing. It's really great for data analysis. But your flight software system just can't really, effectively utilize Python. So what we've been working on at LASP in collaboration with Hans-Peter Schaub at the Autonomous Vehicle Systems Laboratory is an environment that we call Basilisk. And what Basilisk attempts to do is try and capitalize on the potential of Python with flight software. And so there's actually a lot more to Basilisk than just this flight software piece, but as this is a flight software conference, that's what we're really focused on here. So the reason that we named it Basilisk is there's a lot of things. Like, we're very Python-centric, so it's reptilian. Also, there's the South American common basilisk, which is a lizard that runs so fast it can run across water. And so that's really like one of the central intents of the Basilisk environment, is to just crush everything with speed. So we start with C, C++ code, and then we go into SWIG, which stands for Symbol Wrapper Interface Generator, I believe. And what SWIG does is it takes your C, C++ code and runs a preprocessor on them to generate a bunch of auto-generated functions that allow you to effectively use your C, C++ code just like it was Python. Under the covers, a lot of the Python modules are C, C++ code that people have either auto-generated the bindings or used some other tool. We use SWIG because it happens to work well for our use case. We also use Doxygen, which is not really central to the process, but it does create, I'm sure a lot of you are familiar with it, but you put specially formatted comments into your code, and then it can take those comments and generate documentation off of it. It can use LaTeX kind of comments or just regular HTML-based comments, and it generates call graphs and kind of like the design documentation for what you're trying to build. From there, we also go into a program called CMake, and CMake, it's a lot like Makefiles, but the advantage of CMake is it stands for cross-platform make, and that allows Basilisk to kind of run anywhere. So Basilisk can run Windows, Linux, Mac OS. You can use CMake with RTEMS to effectively generate like your RTEMS target or your Linux target if you're using a flight software that can run on Linux. And then that all wraps into Python. So now we essentially have our C, C++ code that we've tried to write as though, exactly like we want to write our flight software, and we can treat that just like Python. So the Basilisk environment is composed of a simulation side, which is intended to model the dynamics of the system. So you have your kind of like, and my background is in Gene and C, so a lot of this is kind of Gene and C centric, but the environment is not Gene and C centric. But my particular use case for it is very Gene and C centric. So you have your kind of like dynamics plant that models your vehicle. Then there's an inter-system message passing interface, and that comes across to your flight software side. So you have like your attitude navigation, your vehicle control, your pointing. Obviously I had to fit this on a chart, so there's more than just 3 models over here. There's more than 3 algorithms over here, right? But the intent of the environment is that you're supposed to be able to just kind of create your Legos. And your Legos interface through message passing to be able to talk to each other. So you can sandbox all of your dynamics messages to keep them over here to prevent yourself from cheating and passing your dynamics information right across to your flight software. And then this abstraction allows you to kind of abstract your flight software. So there was a system that I worked on previously on a different program that really intended to allow you to use multiple different versions of flight software. And you can insert a socket-based abstraction here or shared memory or something to really use different processes, one running your dynamic system, one running your flight software system. The advantage of that is that you can use your kind of ADC system design or your simulator design with real flight software. The power of that being that you sort of have one simulation to rule them all, and you don't get into INT and then you're like, okay, now we bring in our other simulation environment, which duplicates a ton of code, introduces lots of new bugs, and is usually a pretty hard thing to ingest. And usually that dynamic system, it really is intended to run in real time, whereas your ADC system is intended to run in non-real time. So you hit a lot of like unexpected bugs when you're making that transition. So the the Basilisk flight software kind of like capture phase. So we have these Python modules, right? And they are essentially our Lego bricks, and they're folded into different task groups. So you have like say a 10 hertz task and a 2 hertz task or something like that. And one of the advantages of Python is it's very good at doing introspection. So it can look down at itself and say, okay, what am I? Like, am I a cat? Am I a dog? What parts do I have? And it can see, like I have this set of modules and they have these parameters. Where doing that in C and C++ is just about impossible. Like there's no introspection in C. It can't really like look at itself. But Python is great at that. So Python can say, I have a 10 hertz task, I have a 2 hertz task. They have this set of modules in them. Those set of modules have these parameters. And then, for a code generation step, like I wouldn't say it's trivial. It was actually pretty darn hard, but it can actually go and like lay out that kind of boilerplate generic code that, there's not a lot of value added in generating that. It's like, well, I cut and paste these parameters from here, or more likely I hand code it from some fizzer or something like that, and I fat finger a couple and I make mistakes. And the nice thing about the computer is it doesn't really like make those mistakes. And then the messaging map can actually be obtained from a run of the environment. So the environment will run and it will say, okay, what messages got generated? Who generated those messages? Where did those messages go? And sort of after the fact, tell you what the architecture of your system looked like. What is your kind of like topology of the messaging system look like? And the power of that is that a lot of the times when you're building these systems, you have this intent of here's how the vehicle should operate. And it doesn't really matter what you think the vehicle should be doing. It's what you actually put into your system. And frequently there's things that are out of sequence or out of step. And what you can do is like look at this thing post-run and say, does this design reflect what my intent was? And that's all done via a prioritization scheme and salts the modules in where they're supposed to get run according to how you set it up. And then post-run, you can look at what the effect of that design was. So the neat little chart here is the blue line is kind of like an all Basilisk environment where the flight software was run. It was run in 2 processes. The flight software was still in Basilisk though. But for our particular project, we're using CFS and RTEMS for the flight software side. So the green line is actually the CFS running inside the Linux target. And this represents like a safe capture kind of scenario where you start out far from the sun, you come back onto the sun. So you can see that the agreement is pretty darn close. And granted, the dynamics are slow, but the uniqueness is that we have these 2 like pretty different environments. There's CFS, which is a flight software middleware architecture, and then there's this pure kind of Python Basilisk environment. And you can get really high levels of agreement between them, and you can switch them out kind of interchangeably. So then let me see how I'm doing here. The Basilisk environment is further good at doing the testing level kind of business of unit testing your algorithms. So once you have these things as Python scripts, right, or Python modules, you can utilize them in your Python script. And so it's Python, right? So instead of having to like code in, like setting 100 element array to 0, or any of those things that take a lot of code, they take a lot of stubs, or they take a bunch of like stub architecture that you have to bake in, like that's all just available because you're using Python. So you can use tools like NumPy to create these big matrices, and you can set them based on the kinematic math if you want to do that. So it allows you to like quickly set up a test stub and run it. Then post-test you can use those same tools, like we use NumPy and Matplotlib a ton to analyze what the effect of that test was. So the test initializes, you set all of the parameters, those get passed in from Python down to the C level, and then at the end you can extract all the data from your run back out into the Python environment and say, was this test successful? The other really neat thing that you can do, because this is, I tend to run on OS X or Linux, so you can use all of those free tools to analyze what the test suite actually did. So you can kind of envision, I don't know if people are familiar with gprof, but gprof is a Linux tool that tracks the code usage it does, line coverage, decision coverage, MCDC coverage. And so, at a very simple thing, if you've architected the system to do it, and that's how we've architected the main part of Basilisk, is you instrument your code for this tracking, you run your test suite called like py.test. PyTest goes and parses out through the whole directory, finds all the tests that you've created, runs them, and then post-run you can say, okay, what did my coverage look like? Like what percent of my code am I testing? And where are the pieces of dead code? What am I having trouble hitting with my test suite? And then go back, refactor your tests, and rerun. The other really neat thing, oops, Scott, almost there. The other really neat thing that you can do is because it's Python and it works with kind of generic classes, you can have kind of a central test base class. And these are all options. Like it's the way I like to code it, but the intent of the system is to kind of let you treat it as though it's just like Python. You can do anything you want. But you can have a central test base class, and it sets up like, okay, what messages should I log? What variables should I log? What rates should I log those at? What kind of events am I going to have? So when you're operating and you want to change modes, like you can script those via events and say, okay, when these conditions are met, execute this event. So you have kind of a central test base class that can put all of that into one run. And then your scenarios just inherit all of that functionality. So you can say like, okay, do my MOY scenario and give me the trajectory plots, or do my science pointing scenario and give me the nav plots. And that's just a really quick, simple way to analyze what your system is doing. And then we have to do this for the project that we're doing. There's kind of the central part of Basilisk, which is the kind of generic code, and then there's mission-specific code that is unique to our program and also is proprietary to LASP and not to be shared outside of the program. And so you can keep those kind of separate and have two repositories, the main Basilisk, and then Basilisk can just import your additional modules from this separate area. So the test execution analysis, this is something that I've talked about a little bit, but it's really, Basilisk is designed to facilitate analyzing what happened. Primarily we use packages called NumPy, Matplotlib, PyTest. NumPy, for anyone who's not familiar with it, is a matrix manipulation package. It works a lot like MATLAB, where you can create these matrices, you can multiply them, you can look at, you can do like norms against them and decompose them into like LU decomposition, all kinds of matrix math. You can do that inside NumPy. And because of the integration between the flight software emulation and the Python level, you can do that against your flight software objects. And then matplotlib just allows you to generate plots. And this is one that Mar put together, which is really kind of neat. And it's the flight software behavior in a safe capture scenario. So you start off far away, and it captures you back to the sun. And you can tell when the control is on and off, and what the MRP thresholds are for control and everything, and see the kind of like integrated behavior. And without having to jump out of your simulation tool over to some kind of analysis tool. It's all baked into one. So any C++ variable that can be accessible via SWIG can be logged and interrogated. And we haven't found a type yet that I can't make work. Some of them have been pretty tricky. There's this really neat matrix library that we're using on the C++ simulation side that it allows you to kind of like do matrix multiplication and matrix addition and transformations really simply in C++ code. And getting those types to work as Python lists was pretty difficult, but it's really neat in the end. Yeah, and all messages can be logged. So this is one thing that I talked about earlier, where once you've auto-coded the system, or once you've kind of created your system design, I should say, you can analyze like, okay, what happened in this run? So here's the handoff at that message passing interface layer, and we're going to decode some IMU sensors, we're going to decode some coarse sun sensors, we're going to have some vehicle configuration data. Okay, now that all that kind of like SOP information has been processed, now we're going to do a weighted least squares estimator, then we're going to go into sun-safe pointing, then we're going to go and do our steering law, and then we're going to convert that over to RCS forces. So this is really like an artifact of what was run. It's not my design. It's not something that I coded in there. It tells me how my design behaved inside the environment, which is very useful. Like the first time I wrote the routine to be able to display this, like all these arrows were completely messed up, and everything was well, not everything, but several things were pointed wrong, and Dr. Schaub and I were laughing about that because it was like, I just wanted to have this so I could see it and so I could, visualize what was happening. I didn't intend to actually find a whole bunch of bugs with my design, but, that's what happens. So then each Basilisk task at the task level can have boilerplate code generated. It's a lot like when you auto-code your Simulink design, you get these step functions out. And that's what Basilisk returns for you for the Basilisk system, is kind of these step functions for the tasks. But the interesting thing is, like your base code, that's what you hand-coded, that's what you designed, that's what you really, you sit there and you stare and you say like, yes, I really agree with this particular piece of code. And then the boilerplate is, it's much easier to generate that code because it's fairly simple, and it's not as error-prone an operation as generating that hand code. So, you can really focus on what matters, which are your internal algorithms, and not worry so much about that kind of boilerplate connectivity that can be generated by a computer. I'm doing all right. So this is kind of like a simple task, and it fits pretty well into this kind of diagram. But you can get much more complex behaviors as you stack up these Legos. And the diagrams get a little bit harder to read, but they still can give you that same level of information. And then you can really like say, okay, for this specific operation, like my science pointing mode, here is the sequence of what gets run. And then that's easy to share with the rest of your team, and they can say like, yes, that's the design that I agree with. But they don't have to really concern themselves with the low-level details of, what does this MRP steering law do exactly? So these are very helpful diagrams to be able to share across like the wider team, not just inside of the ADC or GNC group. So the intent of Basilisk is to kind of serve going forward for us as a way to develop simulations and a way to develop ADC flight software at least, and maybe other subsystem flight software. But the nuts and bolts of it are that we have a project that we need to execute on. And that project, we've selected RTEMS as the operating system and CFS as the middleware, which is super germane to this conference. And it seems like a bunch of other people are doing that, which is very interesting to me. And so we're using Basilisk for the ADCS application development in that environment. So we have an ADCS application that gets executed by CFS, right? And interestingly, what we found when we brought the autocode into RTEMS and CFS is that the CFS messaging system is just not quite ideal for our use case. The messages that we kind of pass along, the idea is that like pretty much anybody can subscribe to any given message, which CFS is pretty darn good at. But we also kind of want those messages to hang around. So if I go and query a sensor message, I need it to be there when I go to look for it. And if 3 other algorithms have pulled that sensor message down, I don't want it to have vanished from the pipe that I'm using. So CFS doesn't quite work as well there, and we could have like really bodged it to try and get the CFS message pipes to work that way. But then what you end up with is basically any message needs to have a unique pipe associated with it, and there's only 255 of those that you can use. So very quickly you start to run into kind of resource contention issues on the message pipes. So what we ended up having to do is write an internal Blackboard messaging system. And that's fairly simple, right? But it is something that was kind of surprising. Like the idea when we went into this is, well, I know CFS uses messages. I know that we want to do this kind of like, it's a sampling port sort of construct like what ARINC uses. So I know we want to have this construct. I think they'll play great together, and they just didn't. But then, we kind of have this internal ADC messaging system that kind of pushes and pulls stuff from this Blackboard. But then we can selectively mirror stuff out onto the CFS software bus, which is actually kind of helpful, because then the software bus doesn't have quite as many messages flowing around on it, and we can kind of down select the huge volume of data that's available inside the ADC, or relatively huge volume, into specific packets that are destined for other subsystems. And then the autocode insertion into the main ADC app is like trivial. That was from really good work that Mar and another one of the students in HP's lab have done, is to kind of like abstract all of that, all of the kind of like extra wrapper that needs to get built for an individual application into a couple discrete function calls. And so there's a parameter setting. You call the function, it sets like all the parameters inside the system. And then for each rate group that you want to have, there's a couple calls that you need to have to provide the message linkage and then to execute the runtime. This is another like really complex set of behaviors that we're able to build up. And this was done slightly later than that safe mode one that I showed. And I was just like pleased as punch when I saw it, because this is CFS running on the Linux Target, which isn't quite running on the Target, but we're getting there for the project, and I expect to see the same kind of behavior. So there's a little cyan line underneath there, and that's actually the all Basilisk environment. And then the dark blue line is with CFS in the loop. So that's passing star tracker messages over to CFS, CFS doing the attitude determination off of those messages, and then executing all of these sequences. So we come over to the planet, we scan down, we go to the center, we image, we come back over, we scan down, and that's that can all be assembled with these kind of like Lego bricks, and it's done with orbit relative motion. So this is really our scans relative to the planet as we kind of pan around the surface of the planet. And it's really complex behavior that's fairly easy to build up, and then you can verify at the unit level these kind of simple Lego bricks, and not have to that unit verification is really pretty useful, because the boilerplate architecture is very simple. So you go and verify that at an integrated level, and you can have a high level of confidence that there's not a lot of hidden gems in that boilerplate architecture code, because there's almost nothing to it. So where are we going? We intend to release Basilisk open source in mid-January. We're going to do an invitation-based alpha, and that's all being handled by the Autonomous Vehicle Systems Laboratory, being directed by Hans-Peter Schaub. We anticipate doing a full open source beta release sometime in 2017 that will be completely public, and after that we're going to maintain it as a true open source project on Bitbucket. We believe that we have verified most of our simulation level models. There are a couple caveats there, like the base of the simulation is really directed at our missions application. You know, it's not unlike the issues that CFS has. Is, you know, we're not developing some kind of completely generic capability. It's vectored at a particular application that we have. And then all that software is going to be undergoing a CDR review in 2017, and the simulation testbed will serve as the flat-sat driver for our flight program and eventually run the observatory in our final run-up to launch. This is actually a simple or it's not that simple, but a visualization that the AVS team has cooked up for how to look at what the spacecraft is doing. And we anticipate that all that work is going to culminate in a spacecraft that gets launched by late 2020 and hopefully has a great amount of success. So we've created this unique kind of Python-based environment that allows you to do a good job of building your C++ flight software in a really testable and transparent manner. It's very scalable. You know, it comes from my history of designing these simulations and designing these GNC systems, from like very simple test beds that you can put together in like 20 minutes up to, you know, like a full vehicle simulation that's running hardware in the loop simulation. You can run it on just about any PC out there. I regularly test on Windows, OS X, and Linux. I use Mint because it's tasty. Everything that I've shown in this presentation, it's free. So you can get Python for free, you can get CMake for free, you can get Swig for free. You don't have to get a special release from NASA to get any of these things, which is just freaking awesome. You know, I run it on my home computer. I run it on my work computer because it is, you know, it's trivial to get these packages. And like honestly, I haven't even gone over some of the coolest parts of the Basilisk system, like the underlying dynamics of the simulation. That is one of HP's like big things. Is like this, the dynamics need to be right, like not just close, but right. So like angular momentum, orbital momentum, those need to be conserved to the machine precision. And those are just not requirements that I've ever really intended to honor before in my career. But we have good tension, him and me, and you know, we've ended up with some really cool, really powerful analysis capabilities. So that's it for me. Questions? Oh, and that's our logo. That's the South American common basilisk.
Since there's an auto generation step, how do you debug the integrated system?
So the auto generation step, you can generate that kind of like top level boilerplate, right? Mm-hmm. And so then what I like to do with that is I then swig that back into Python. And so all of my parameter settings, all of my task layout and everything is then happening in that C++ code. But I still, you know, I'm still kind of swimming in the happiness of this Basilisk environment where I can log things, I can view things, I can debug things. And then once I'm satisfied with that performance inside Basilisk of the whole auto-coded integrated system, at that point I'm ready to drop it into you know, CFS or wherever it's intended to go with a high level of confidence that it's going to work.
So you debug in that environment and then you go back to your source and change it?
Oh yeah, like if there are algorithm bugs, but we debug the algorithms at the kind of like base all Python environment because you can attach any debugger to Python, and you just break right down into your code. And so like at the algorithm level, that debugging is very simple. And it's easy to step through your code, and then you debug kind of like the integrated boilerplate performance at that higher level. The idea being that you shouldn't really need to debug your algorithms. And obviously, you still have to a lot of the time, and you can still debug down into the algorithms and GDB or breakpoint in there, and then debug the integrated performance inside that system. And you can do the same thing with CFS. It just, it gets increasingly painful. I'm sure like all of us have experienced. As you walk through that depth, it gets much, much harder, but the idea is that we can debug across the whole stack, and we can compare run to run between the different environments.
All right. Thank you. Oh.
We have an online question from Sebastian Garcia, who asks, are you considering any specific hardware target, HHWIL, etc.?
Not sure how much I can say about that. Yes, we are considering a specific hardware target. We also intend to test on like your kind of ARM platforms like BeagleBone and Raspberry Pi, just to make sure that it does cleanly get there. And then we have a specific hardware target for our mission that's based on a radiation-hardened flight computer.
All right. Thank you, Scott.